I'm Andrew Giles and I'm the CEO of the Garvan Research Foundation. Thank you all for coming along for our 3-minute thesis. You may have noticed the judges in a huddle because we were hoping there'd be a trapdoor so that at the 3-minute mark you would plunge down to your death, but unfortunately that's not going to happen. Let me tell you who our judges are. Professor John Shine, who you all know. Sophie Scott, award-winning journalist. Josh Yen, very brave individual for coming along. Do you know the rules of the 3-minute thesis? No, good. Good luck, there's a whole slide on it. Just 3 minutes. So it's called the 3-minute thesis. So how many minutes do you have?
3.
3! Not 4. Not really 2, actually. And certainly not 5. Alexandra will walk up and whack you in the face if you go too long, but there is no buzzer. So you need to know on your internal timing, is that right? That 3 minutes is up?
Waving.
Alexandra will wave at you at the 3-minute mark. The judging criteria, your communication style, your comprehension, and your engagement with the audience. Hang on, are we about to start? Is that the next slide? Prizes! Yes, well, let's get to the money. There we go! $300 for first prize, $200 for second prize, $100 for third prize, and more importantly, you get to compete in the Faculty of Medicine 3-minute thesis heat. Talk.
3-minute thesis would be a good one.
Yes, it's true. All right, the first person up. Do they know who's coming up? They know the order. So when I say Gemma, you're going to go, yay, great, I'm excited. Woo! All right, so the first one up, Gemma Pearson, recycling facts to treat diabetes. The down arrow will get to your one slide.
Thank you, Andrew.
No, thank you.
Thank you. Okay, so good afternoon. My PhD thesis revolves around pancreatic beta cells, which are a really important part of your body. These super smart cells are solely responsible for the production of the hormone insulin. And why is this important? Well, when we eat a meal, our blood sugar levels rise, and our beta cells release insulin in response to this. This is so that all of the other cells in your body can use this sugar as a fuel, so that they can function normally. If we don't produce enough insulin, we develop a condition called diabetes. Diabetes affects approximately 4% of Australian population, and it puts people at risk for heart disease, blindness, and even premature death. So it's vitally important that we can understand the exact processes by which these smart beta cells can sense changes in sugar and release the appropriate amount of insulin. And this is where my PhD comes in. One way that these beta cells can do this is by using their internal fat stores. And I'm particularly interested in how the lysosome can affect these stores. The lysosome is a vital part of all cells. It's basically the recycling factory of a cell. Many different substances are delivered to the lysosome, including fats, where they're then broken down. Much like a recycling plant will receive paper, plastic, and even glass bottles, which they can then be broken down and reused as new products. I've shown for the first time in my research that if you block fat breakdown in the lysosome, you can increase insulin release in response to sugar. Now obviously, there are many different ways that fats can be used and broken down within a cell. So when I stop them being broken down in the lysosome, I force them to be used in a different way. Much like if all of a sudden tomorrow we stopped recycling glass bottles, we'd suddenly have to come up with a new way to deal with all these excess glass bottles. In the case of the beta cell, using fats in a different way means that they can release more insulin in response to sugar, which I think is pretty smart. Going into the future, I hope that my research can be used to develop new drugs which target this recycling of fat in the beta cell and maybe generate new drugs for the treatment of diabetes. Thank you for your attention.
Thank you, Gemma. That's great. Off to a flying start. Carol, are you up for the challenge? 3 minutes. Alexandra is monitoring the clock. A new therapeutic target for pancreatic cancer. Your one slide is 1 arrow down.
Cancer. It's a powerful word, and it's also a terrifying one. But follow the word cancer with survivor, and the fear associated with that word is overcome with empowerment. Cancer is, at its most fundamental definition, malignant growth. The malignant growth of our very own cells. No wonder it's terrifying. But how do our own cells go from being in a state of normality into transforming into these malignant cancer cells? A part of that answer actually exists within the cells themselves. Cells are not hollow spheres. They are filled with numerous components, such as DNA and proteins, that ultimately dictate how our cells react and what our cells become. Now, my PhD project aims to identify those components within our cells that can turn them cancerous, because those components are the very ones that we should be therapeutically targeting in order to develop more efficient and more effective cancer treatment strategies. Now, I specifically work with normal and pancreatic cancer cells. Pancreatic cancer is one of the most lethal of human cancers. A staggering 95% of pancreatic cancer patients die within just 5 years from the time that they are diagnosed, and most within the first year, because pancreatic cancer cells are just so characteristically invasive. You see, growth is just one aspect of cancer. Cancer cells can also invade. They can invade our blood vessels and our lymph nodes, and then use these vessels to travel, to spread, to create secondary tumors in nearby organs, quite often in the liver in the case of pancreatic cancer. To cut a long story short, I'm going to take you straight to one of my discovery results. Essentially one of those potential cancer-causing cellular components, a protein called SGK223, which I will now refer to as protein S for the remainder of my talk, allow normal pancreatic cells to produce more of this protein S, and they transform. They transform into their invasive derivatives. Now, what does that ultimately mean? I found that protein S induces pancreatic cells to invade. Therefore, protein S is a potential new therapeutic target for the characteristically invasive and devastatingly lethal pancreatic cancer. Thank you.
That's great. Thank you, Carol. The challenge has been laid down. Amy, are we ready? Where's Amy? Amy, right. Hang on, sorry, I got to press the button. To eat or not to eat, that is the question. Your one slide, your 3 minutes starts. As soon as you press the button, down.
Okay.
Press the button
I
down.
pressed it.
Go.
Do you ever wonder what makes you crave a delicious hamburger? Or what makes you say yes to, would you like fries with that? Your brain is a powerful tool and is the key to answering this question. My PhD looks at the interaction between your brain and saying yes to eating. Our continuous yeses, more often than not, to food have caused billions of people worldwide to become overweight or obese. As most of us know, obesity causes severe morbidity, leading to other health issues such as cardiovascular disease and diabetes. Also, obesity places great financial burden on international economies, costing Australia alone $120 billion every year. Additionally, the vast majority of previously developed obesity therapeutics have been suspended due to negative health side effects or just simply do not work. In this lies a large and critical demand for an effective and long-lasting obesity treatment, and fast. This is where my PhD comes in. I look at a neurotransmitter that your brain naturally releases called neuropeptide Y, or NPY. NPY is one of the most important regulators of your metabolism. NPY has two fat receptors called Y1 and Y5, and these cause you to gain weight. These fat receptors do this by making you say yes to eating, increasing your drive to eat, therefore increasing your feeding. This leads to increased fat accumulation in your body and that dreaded obesity. My PhD hypothesizes that by blocking these fat receptors in the hypothalamus, or your brain's eating center, we are able to make you say no more often, therefore treating obesity in a never-before-seen method. I work with a genetically modified mouse model, and I have used this to recently show that by blocking these fat receptors in the brains of mice, we are able to make them say no, reducing their food intake. So by utilizing this method, similar to building a brick wall between your brain and your appetite, we can make you say no more often to that hamburger and those extra fries, therefore showing that this method has great potential as an effective and long-lasting obesity treatment. Thank you.
Thank you, Amy. Amy Corkindale. How to use stop signals to go down the path of heart development. Go.
What would you do if you had a heart attack right here, right now? Luckily, we're quite close to the hospital, so you might be okay for the short term. But you could have lost up to 1 billion cells in your heart. So long term, you're going to have problems. If you scratch your arm, your skin cells will migrate to the surface, divide, and heal the wound in a number of days. But unfortunately, a heart attack victim is not quite so lucky. This is because our beating heart cells only divide once every 10 years. So if you have a heart attack, how can we possibly make new ones for you? That's what my PhD project is trying to answer. When the embryo is in its first few days of growth, there's a small mass of cells within. These are the embryonic stem cells. And the embryonic stem cells eventually form you. We have trillions of cells in our body, and each one has its own specialized function. But despite looking and behaving very differently to one another, all of the cells in our body came from one type of cell, the embryonic stem cell. Therefore, every cell has the same DNA. But how do different cell types know which genes to use? We know that within each cell, we have a set of chemical instructions. These instructions overlay the DNA, leave a mark, and this turns unwanted genes off. This process is called epigenetics. I study where the epigenetic marks, or stop signals, are placed along the DNA in different cell types. I grow embryonic stem cells on a petri dish, where they'll divide indefinitely. But if I change the growth conditions to mimic development of the embryo in the womb, I can induce cell specialization. After a few days, if I look down the microscope, I can see sections of cells beating away. These are cardiomyocytes, or beating heart cells. I call them my little beating hearts. So back to you and your damaged heart. If I know exactly where the epigenetic marks are placed in beating heart cells, I could take your stem cells, artificially express these stop signals in your cells, and grow you new beating heart cells. This may sound like a fairy tale, but hopefully in the not too distant future, I could mend your broken heart.
Sophie, metabolism in the driver's seat. Boom.
I've
discovered a trait common to both fat cells and cancer cells, which has revealed a new way to tackle cancer. Most people don't like fat cells, but there's something they are really good at. Fat cells are really good at responding to insulin signaling. They are one of the best cells types there is to do this. And signaling, insulin signaling tells the fat cell to take up glucose from the bloodstream. So signaling controls the cell. It tells it what to do. It's like if the cell was a bicycle, signaling would be the rider, making it go forward. Cancer cells are also really good at signaling. And they are so good at signaling, in fact, that they are always have their growth signaling pathways active. And this is what makes them continually grow. All cells use glucose to make energy, and cancer cells need a huge amount of energy to maintain their constant growth. But cancer cells use glucose in a very strange way. There are two pathways that can be used to get energy out of glucose, and cancer cells prefer to use the more inefficient pathway. The longer pathway is most efficient, and the shorter pathway is highly inefficient. If you think of the two pathways as a slot machine and glucose is money, you put one glucose dollar into the longer pathway and you get 36 energy lollies out. If you put one glucose dollar into the shorter pathway, you only get 2 lollies out. So it's a great mystery why cancer cells prefer to use this short, inefficient way to get energy out of glucose. I was really surprised to discover that fat cells also use this short pathway. So why do fat cells and cancer cells like to use glucose so inefficiently to get energy? I looked for something else that was in common between these two cell types, and I found that both cancer and fat cells have a huge amount of one particular protein. I wondered what would happen if I put this protein into normal cells. And I was amazed to find that this protein forced the cells to switch to the short form of glucose metabolism. And not only that, but it increased their sensitivity to insulin. So they were super sensitive to signaling, just like cancer and fat cells. So if we go back to a cell as a bicycle and signaling as the rider that makes it go forward, then I've found a way by increasing the short form of glucose metabolism to pump up the tires and make the cell go faster. So if we use drugs to target this short form of metabolism and block it, we can deflate the tires on cancer cells and stop them in their tracks. Thank you.
Thank you very much, Lucy Yang. Seeing the Invisibles, and you're on.
Hey, check out my exciting result on this slide. It's so obvious that this tumor is driven by this protein here. And this protein is helping the tumor to escape the death signals. And that explains why our previous treatment didn't work. So now we know what's happening in the tumor, we can design personalized medicine for this patient and to save a life. Isn't it fantastic? You know what I'm talking about? Oh, that's right, because you don't have the tools in my hand to see this picture. Sorry. I know this is frustrating and annoying not being able to see anything, but this invisible picture is exactly what our doctors can see in many situations where they have to make a decision, a treatment decision, which may mean life or death to the patient. And there's nothing to help them decide what will work for their patient, as each cancer case is different. Using pancreatic cancer as an example, no more than 10% patients receiving the standard chemotherapy actually respond to it, and less than 20% can make it through the first year. So that's very sad and serious. So my PhD decided to tackle this problem by developing a tool which will allow us to see this invisible picture. So what are these guys? They are a group of protein called protein kinases, play a very important role in our body to keep us healthy. Sometimes they may misbehave, and when this happens, that may lead to numerous diseases, including cancer and diabetes. The good news is, many of these diseases can be treated by targeting the misbehaving protein kinases. But then, which ones? There are more than 500 of them in our body, but found at a level very low compared to the vast majority of other proteins. So in order to see them, it's just like finding a needle in a haystack. I wish we had a magnet for it. A magnet. That's exactly how my tool works. It acts like a little magnet, recognize protein kinases instead, and capture them, isolate them from the rest of the proteins, allow us to examine them. I apply my tool in some cells, and we achieve the largest number of protein kinase identification ever reported. I also apply this to generate kinase profile in some healthy cells and some cancer cells, and the comparison of the two highlighted some misbehaving protein kinases, which may hold the key in treating this cancer type. Currently I'm making my tool available for doctors and researchers across the globe. And I believe my PhD project that allows us to see this invisible picture, this part, would take us one step closer to achieving personalized medicine and to save more lives. Thank you.
Right, so Lucy's broken the machine.
That's not what you're supposed to see.
Here we go. Louise! Louise! Welcome on board. Prader-Willi syndrome, when too much is not enough. I won't even touch it now. Just use that one. Yeah, that's fine.
Imagine you've just eaten a huge Christmas lunch with heaps of turkey and plum pudding. Could you eat another meal straight away? If you had Prader-Willi syndrome, you could keep on going all day. People with Prader-Willi syndrome have a genetic condition which causes them to have an insatiable appetite. If not supervised, they can literally eat until they die of gastric rupture. And there's no pharmaceutical treatment against this. The only thing that works against it is constant supervision and locking up all food at all times. So my PhD project aimed to find out what drives this appetite. Because once we know which hormone or brain pathway is behind it, we can use this knowledge to develop a treatment. So first, I wanted to find out exactly how the meal response works in people with Prader-Willi syndrome. To do this, I studied a group of adults with Prader-Willi syndrome and a group of healthy control subjects. And I used a visual questionnaire to progressively measure both hunger and fullness before and after a meal. Now most people, before they eat a meal, feel hungry, of course, and not full at all. And then after they eat, they feel full, but not hungry. I found that people with Prader-Willi syndrome did feel full after eating a meal, but their hunger levels didn't drop at all. So even after eating a very big breakfast, they felt full and hungry at the same time, which is a very difficult feeling for us to imagine. Now what this tells us is that people with Prader-Willi syndrome don't have a problem with their fullness response to food. Instead, there's something wrong with the way their hunger pathway is regulated that causes them to feel hungry all the time. Now when I investigated the physiology of these people further, I found three things that were different to healthy people. A hormone called ghrelin, an immune molecule called IL-6, and sympathetic nervous system activity. And these are all things that are involved in the regulation of food intake, and they could all be potential targets for future anti-appetite drugs. What's interesting is that I identified defects in 3 separate systems. The endocrine system, which regulates hormones, the immune system, and the nervous system, which shows us that Prader-Willi syndrome is a disease with a very complicated basis. And it means that any future treatments for anti-appetite in Prader-Willi syndrome will need to be a multi-system approach. Thank you.
All right, so the first thing to say is we were absolutely delighted with the quality of all the presentations. The Garvan Research Foundation obviously put up some funds to provide the first 3 prizes, and we are so delighted with the standard of them, so we will double the value of all the prizes, because I think they really are amazing, and obviously next year it'll get even harder, but it was all the effort you put into it was gratefully appreciated, so thank you very much. One of our judges, Sophie Scott, is going to give you the winners, and you can have as much time as you'd like. You can have half an hour, 40 minutes, we don't mind.
No, that's fine. No, I'm used to
3 minutes.
a minute 30 is my usual time slot, so I'll try to keep this to a minute 30. So yeah, I just want to reiterate what Andrew said about the quality of the presenters, and they were all fantastic. Great communicators, obviously great scientists, and I think they've all got a really bright future in the work they're doing and being able to communicate it to a lay audience, which is crucial in this day and age. So we had to choose 3 winners, and we were we actually all agreed fairly easily, the 3 of us. We all there were people that stood out as really exceptional in explaining the science of what they're doing. So again, they were all excellent, but there were 3 that we believe were just slightly above the cut in terms of explaining the complicated science to a lay audience. So I'll do it in order of 3rd, 2nd and 1st. The 3rd prize winner is Gemma Pearson. And the comments that I wrote down were, it was a simple explanation, good analogy of the recycling factory, which made it really easy to understand, and a really good analysis of what the future applications of this research could be in the future. So well done, Gemma. Our second,
200 bucks in.
yeah.
Thank you, John.
I learned you've got to remind him.
Our second prize winner is Amy Newen, to eat or not to eat. And the reason that the judges and I really liked this was because it brought it back to basics. Why do we crave food? You know, how does the brain work to make us crave food? And what new understandings Amy could bring to that debate, and some really exciting scientists. Again, we thought the brick wall analogy was a really good one, simple to understand, and also again that she was really good at explaining the future potential of this work. So we thought Amy did really well. So congratulations. And our final and 1st place winner for the competition is Louise Pertel, the Prader-Willi syndrome, when too much is not enough. So we thought Louise did really well. Again, being able to bring it down to a level that anyone can understand. You know, imagine eating a big meal and then 5 minutes later feeling like you wanted another meal. But I think what really got Louise over the line with this was that she was able to explain quite complicated science in a very simple way. You know, the things that she'd identified in her research, the defects in the systems that were going to be have to be fixed for this problem to be fixed. And so it wasn't going to be one simple, easy answer. There was a complicated problem, but she had some really good and innovative solutions. And she definitely left us, or me, wanting to know more about her work. And I think that's what a good scientist and a good science communicator does. They can explain things well, and they can leave you saying, wow, that was really fascinating, I really want to know more. So congratulations, Louise.